Hi, my name is Samiya and welcome to my presentation on magnetic vine robots for minimally invasive surgery. This presentation covers in its entirety what I would have done over the past 7 weeks for the CariSurg Research Internship Program for 2025. For me, this program was very engaging and it taught me a lot about the importance of robotics to the medical field and enabled me to develop and grow my technical skills on a higher level. I hope you can enjoy my presentation. So first, what exactly are these vine robots? If we start at the beginning, vine robots, as their name suggests, actually draw their characteristics from the vine plant. These robots are a class of soft robots which mimic the movement of the vine plant, which grows by extending from its tip to navigate through dense and complex environments. In a similar way, vine robots grow by everting their tip in an outward motion, allowing the robot body to maneuver through intricate spaces. Like the vine plant that is resilient to its environment, vine robots embody this characteristic, which makes them versatile and adaptable to their environment. Unlike traditional robots, which are usually rigid and have fixed movement, soft robots are constructed from adaptable materials and can navigate haphazard surroundings and offer gentle, non-invasive movement. This unique property makes them suitable in medical applications where precision and minimal damage to the patient is critical. So, what was my project aim? My overall goal is that I wanted to achieve vine robots that were suited for improving minimally invasive surgery. This is because the current issue is that existing tools struggle to reach deep areas within the body without causing trauma or harm to the surrounding tissue, hence leading to delays in critical surgery. Therefore, my project aim was to experiment and evaluate these vine robots at minimal size without compromising their operational efficiency. My objectives were to compare the performance of different vine materials, test various diameters with different growing fluids, and identify any limitations and operational boundaries. The clinical relevance of my research covers the safety and advantages of the vine robots. As you can imagine, as the vines grow and invert, there is some level of friction that needs to be overcome to actually be able to achieve steady growth. And especially when working with vines at smaller diameters, this friction becomes a lot higher. Thus, one can actually utilize different growing fluids to change the interaction between the vine's material and its surrounding channel. Secondly, you'll notice the human body doesn't conform to one standard shape, and as a result, certain areas within the body are very complex and narrow, and in general, in order to get a tool into these areas without the use of robotics is extremely difficult. For my experiments, it's important to note that the body of the vine robots must be both flexible and be able to support the movement of the tip without causing permanent damage to the material. For efficiency, the materials I used were both low cost and readily available thermoplastics, such as low density polyethylene and thermoplastic polyurethane. These materials allow for the repeatability of the experiments, which I conducted using growing fluids such as air, water, soap and water, and baby powder. And the diameter of the vines I worked with were 8 mm to 2 mm. For my experiments using air, I would have utilized a very standard experiment setup using apparatus such as an Arduino and pressure sensor, a webcam, pressure regulator, a ruler, and a string and a syringe. While collecting my data, there was some relevant data that I used for my analysis. So these would include the minimum and absolute pressure. This is the first pressure recorded at which eversion begins and is measured at 2 mm. Next was the minimum gauge pressure. This is the actual pressure applied that initiates growth and is calculated as the minimum absolute pressure minus atmospheric pressure. Next was the steady state growth pressure. This is the pressure required to grow the full length of the vine to approximately 150 milliliters. And lastly, bursting pressure. This is the pressure at which the vine ultimately bursts. For my experiments using water, I would have used approximately 10 milliliters of water, which was inserted into the tube, and this tube was held at a declined angle. This was to avoid any water settling in place. For these experiments in particular, it's important to note that both the vine and the tube must remain wet at all times before conducting the actual experiment. For my data of analysis, as you can see in this graph, which shows the relationship between the minimum initial pressure and the vine diameter for different fluids, this is essentially showing how much starting pressure is needed to get the vines to begin diverting for each fluid type. In general, these statistics were important because, as you can see, fluid choice can drastically change how much pressure you need and thus can impact safety. Too high of an initial pressure could risk tissue damage or a rupture, so knowing the right combination of fluid and diameter is critical. In the second graph, it shows the comparison between the minimum initial pressure and then the full growth pressure needed to go to the full length of the line. As you can see, a key takeaway for this was that the gap between the starting pressure and the full growth pressure is largest at the smaller diameters, suggesting that once growth is initiated, larger vines need less pressure to fully extend. This means that for applications where efficiency is key, using larger diameters could reduce the pressure demands that you need, though this is at the cost of flexibility and being able to maneuver the vines. Now, some limitations that I may have experienced while I was conducting my experiments would have been coming down to the type of materials that I use. Different materials actually react differently to their environment and therefore require different settings in order to achieve a good enough seal to successfully be able to grow the vines. So in most of my experiments, I would have used TPU, and in my testing for LDPE, I did encounter some challenges in achieving the seal, so I had to run a number of different tests before I was actually able to carry out these experiments. Here I am showing the example of comparing different seals, which you need to be able to essentially decipher before you can actually start using the material. Finally, practical applications on my vines, I actually tested them using phantom models. These phantom models are simulated parts of the body that I would have tested the vines in. In this case, I'm showing an example of how the vines are able to overcome tight bends, which we normally would be able to do without them. And as you can see now, navigating these tight spaces is easier. Even in collapsed channels, you're able to navigate. And I also explored ways to control the movement of the vines. And one way I would have done that was using magnetic steering. As you can see, there's two different ways, using a permanent magnet and an external magnet. For future work, data would need to be collected on the performance of LDPE using the different growing fluids and at the different diameters, and also a prediction modeling method could be designed. This modeling method would essentially be a way to predict based off of the growing fluid, the diameter, and the type of material you're using, how the vine would react. This way, this would avoid you needing to carry out a number of different experiments. You'll be able to just instantly predict. Thank you for listening to my presentation. I hope you were able to enjoy and also learn along with me. Thank you.